Today we'll be talking about how to compute integrals with the residue theorem. So recall the statement of the residue theorem. If you have a typical curve contained in a domain of an analytic function, and the interior of that curve is also contained in the domain, except at a finite number of isolated singularities, then you can compute the integral of f around that closed curve as 2 pi I times the sum of the residues at those isolated singularities. So the picture is that like your curve is like this, oriented counterclockwise, and you might have some singularities inside here, but everywhere else inside the curve your function is analytic, and the function is analytic along the curve itself. And so that's how you can compute this integral as a sum of the residues times 2 pi I. And just to recall, the residue of a function at an isolated singularity is you take the integral of f around the boundary of a disk of small radius and divide by 1 over 2 pi I. So that's some kind of local quantity. So it's for any sufficiently small r. So you can take your r arbitrarily small. So somehow it's kind of focusing in on that singularity, telling you something about your function around the singularity. And we've seen, so that's the definition of residue. We've seen alternate ways of thinking about the residue. One is that if you expand your function into a Laurent series in the punctured disk around Wj, then the residue of the function at that singularity is just the -1 coefficient in that Laurent series. So that's one way to compute the residue, is if you have a Laurent series on hand for your function. The other one is if you have a pole. So in the case where your singularity is a pole, you can write your function as an analytic function divided by z minus wj to some power m, where that function k is analytic, and then your residue, you can compute that as a multiple of the m minus first derivative of that function k at the point wj. So those are both good formulas for computing the residue, and you see that this residue really is something that's sort of characteristic to the function and the point wj. It's really localized to that point wj. So the residue theorem is pretty remarkable. It tells you that you can compute this global quantity, this integral here over a curve, by just summing up all these local quantities around the singularity. And those local quantities, they're easily computed by other means that don't rely on integration. So practically speaking, you'll always be able to compute the residue without integration. So you have a way of solving these integration problems without actually doing integration in complex analysis. Okay. So we're now going to look at some applications to computing definite integrals using this residue theorem. So here's the first taste of an example. This is somewhat familiar. We've done examples like this, except this is just slightly more complicated. So we've done an example, a number of examples like this using Cauchy's integral formula, but now we're going to use the residue theorem. Okay, so here's an example of an integral that you might try using the residue theorem. So this is an integral that any Calc 2 student could understand, but might have trouble trying to evaluate. And so here we have a new method of evaluating it. So the basic first step is to take that cosine and express it in terms of exponentials. So our cosine is 1/2, so we have e to the I theta plus e to the minus I theta over 2, and then we have the square there. Okay. So let me just write this out a little bit more. So we have 2 plus, we have a 1/4 and an e to the I theta squared, a plus 2, and a plus e to the minus I theta squared. And then a d theta there. Right, and then one thing we can do right now is just multiply top and bottom by 4. So I'm going to get rid of that 1/4 there. We have an 8 now here, and we'll put that 4 up top. Okay, and so basically we're going to make a substitution here. So we're going to basically interpret this as the integral around the unit circle. So our interpretation is that our z is e to the I theta, where theta is between 0 and 2 pi, so that dz is I e to the I theta. So what we'll do here is, so substituting that in, so this is the integral around the unit circle. So what we have to do, so we want to see our dz is I e to the I theta d theta. So we want to see at least an e to the I theta d theta in the original integral. So what I can do is I'll multiply by e to the I theta, let's make it I e to the I theta, and then I have to multiply by 1 over I as well, and I'm going to have to multiply this entire denominator by an e to the I theta. Okay, so what we see here is that this is going to be our dz, and then we have a z squared here, so this is going to be z. This is a 1 over z, and this is a z here. So right now we have 1 over I 4 dz over, now I have this whole denominator up here, but then I have the times z out here, so I'm going to have, and so I have 8 plus 2, that's 10, and then times z, so I have a 10z, I have a z cubed, and I have a 1 over z. Okay, so I have to multiply everything in there by z, and to clean that up a little bit, it'll be cleaner if we don't have that 1 over z in the denominator, so I will multiply by z over z, and now we have z to the 4th plus 10z squared plus 1 in the denominator. Okay, oh, and just one more thing that'll make it easier. Let's take this 1 over I, and let's make that a negative I, and that'll go in the numerator, so minus 4iz, and let's take that dz and put it over here. Okay, so this function we'll call f of z. Okay, so we're trying to integrate that f of z around a closed curve, which is our counterclockwise oriented unit circle. Okay, and so we apply the residue theorem. So our integral of f of z dz, this is a sum, so it's 2 pi I times the sum of residues of our function wj, over wj, the wj that lie inside the unit circle. Right, so we have to find the singular points that lie inside the unit circle of our function f. And that's going to be where the denominator is equal to 0. So we need to find, so need to know z such that z to the fourth plus 10z squared plus 1 equals 0. Okay, and this, so this polynomial here, this is z squared plus 10 times z squared plus 1 equals 0. It's a quadratic in z squared, right? So this quadratic, you can just use the quadratic formula and you can find that it factors like this. So it factors as z squared minus -5 plus 2 times square root of 6 times z squared minus -5 minus 2 root 6. Okay, so basically the quadratic w squared plus 10w plus 1 has roots -5 plus 2 root 6, that's this thing here, and -5 minus 2 root 6, that thing there. So your w is z squared. So it's, okay, so that factors like that, and so so setting that product equal to 0, what we find is you have z squared equal to -5 plus 2 root 6, and z squared equals -5 minus 2 root 6. And what you can notice is that 2 root 6, when you square that, you get 24, which is less than 25. So that tells you that, and 25 is the square of 5. So that tells you that 2 root 6 is less than 5. So this first one, -5 plus 2 root 6, that is less than 0. So z, that's going to be equal to plus or minus. So in other words, if we, maybe I should say it this way. So you should think about this as -5 minus 2 root 6. So 5 minus 2 root 6, that's positive. And this other one, that's -5 plus 2 root 6. And clearly 5 plus 2 root 6 is positive. So z is plus or minus I, that's the square root of the negative, and then square root of 5 minus 2 root 6. And z over here, that's plus or minus I times square root of 5 plus 2 root 6. Okay, so these, so let's say z1, or maybe I'll say w, so we'll call them w's. So w1, that's equal to, let's say that's equal to the I times square root of 5 minus 2 root 6. Then w2, that's negative w1, and that's also the same thing as w1 bar. The conjugate of w1, since that's a purely imaginary thing. And we also have w3 over here. We'll say that's I times square root of 5 plus 2 root 6. And similarly, w4 is negative w3 and also w3 bar. Okay. So remember that the whole point of finding these solutions to this equation was to locate the singular points that were inside the unit circle. So we need to know which one of these w's are inside the unit circle. And for that, so clearly this, right, so the w3 and w4, the distance from the origin there is square root of 5 plus 2 root 6. And 5 plus 2 root 6 is bigger than 5, and so its square root is bigger than the square root of 5, which is bigger than 1. So those are too far away. And so looking at the other two, we'll see that those are inside the unit circle. So W1 and W2, they have the same length, so let's just look at W1. Well, W1 is, so we have to look at the square root of 5 minus 2 root 6. And the key thing is that 2 root 6, the square of that is equal to 24, which is less than 25 and bigger than 16. So that tells us that 2 root 6, that must be between 4 and 5. Right, so if we look at 5 minus 2 root 6, that must be between 0 and 1. And so if we take the square root of it, it's between 0 and 1. Okay, so the magnitude of square root of 5 minus 2 root 6 is between 0 and 1. Okay, so W1 and W2 are the singularities inside of the unit circle. So what we have here is that our integral is going to be 2 pi I times the residue of f at W1 plus 2 pi I times the residue of f at W2. Okay, so let me cordon that off. Okay, so the residue of f at W1. So let's take a look at that. So to compute that residue, what we're going to use is the formula here. So I want to try to write my function in this form here. Okay, so I want to look at that singular point W1. I want to sort of factor out some power of z minus W1 in the denominator. So my f of z, so let's see, so f of z, that's negative 4i z over that polynomial there, z to the fourth plus 10z squared plus 1. But notice I factored that down here. So we factored it, so let me point that out here. So we factored it here. And then we further factored each of those things. So like the z squared minus that negative 5 plus 2 root 6. The roots of that polynomial are W1 and W2 by our calculation. So that polynomial there must be z minus W1 times z minus W2. So for example, so we're writing this fourth degree polynomial in the denominator here. I can write instead, I got z minus W1 times z minus W2. So that's that first one in blue, and then the other one here, similarly, we can write that as z minus W3 times z minus W4. And so we found all the roots, so we've effectively factored it into linear factors. And it'll be cleaner since, see, these two factors here with the W3 and W4, we only care about W1 and W2, so it'll be somewhat cleaner if we just combine them. And what we can use is that W4, so W4 is the same thing as W3 bar. So this is minus W3 bar, so z minus W1, z minus W2. So we have z squared, we'll have plus the norm of W3 squared from that, but we also know that W3 W4 is negative W3, so this is also plus W3. So that means the cross term, the O and the I and the FOIL just gives 0. So in fact, this is our product here. It's just this z squared plus norm W3 squared. Okay, and so our function here is, so we can consider this. So we can consider this our k, and so this is our k of z. And so we have k of z divided by z minus W1. And so the residue of f at, let me see here, sorry, right. So the residue of f at W1 is just equal to the value of that k at W1, right? So we just have minus 4i evaluated at W1 over z, so W1 minus W2, but W2 is minus W1, right? So that's actually just 2W1, and then W1 squared plus norm W3 squared. And an interesting thing happens, which is that this is actually the same thing as the residue of f at W2. So if we look at the residue of f at W2, we use this same form of our function up here, except now instead of the red part is our k. So now instead of the red, this eraser is not good. So now instead of that red, we can use so we have this part, and that's going to be our k when computing the residue at W2. And so again, we get negative 4i W2 over, let's see, we have W2 minus W1, but W1 is negative W2. So that's just going to be 2W2. And then we get W2 squared plus norm W3 squared. And in each of these formulas, you get a cancellation of the 2 with the 2 and the 4. W1 and W1 cancel, and then the same thing, you get 2 and the 4 canceling with that 2, W2, W2. And what you can notice is that these are exactly the same because W1 and W2 only differ by a minus sign, so when you square in the denominator there, those give the exact same thing. So these residues are equal. So our integral here, which was equal to the sum of these two residues, is actually just 4 pi I times the residue of f at W1. So our integral of f at dz norm z equal 1 is 4 pi I times the residue of our function f at W1. And we just compute this, so we can use our computation here. We get, so in the numerator we have of the residue we have a minus 2i, and multiplying that minus I and I is just 1, so we're going to have 8 pi. So we have 8 pi over W1 squared plus norm W3 squared. Right. And we can simplify this a little bit. So 8 pi, so W1 times W1, well, W1 is negative W1 bar. So I can write this as norm W3 squared minus norm W1 squared. And norm W3 squared, if you reference W3 here, that's going to be the norm, you can ignore the I, and then you're just squaring that square root, so that's 5 plus 2 root 6. And then W1 squared, your W1 here, the norm, you could ignore the I, and then you just have minus 5 minus 2 root 6. And so the 5's cancel, you get a 4 root 6 on the bottom, and so you just get 2 pi over root 6 as the final answer. And remember that integral, that was actually computing the integral here, 0 to 2 pi of 1 over 2 plus cosine squared. So the final answer is 2 pi over the square root of 6. Okay, so now we're going to look at computing some indefinite integrals using the residue theorem. So the first class of examples is going to deal with rational functions, so quotient of polynomials, and our denominator polynomial is not going to be 0 for any x in R, right? So that this, so our function is continuous on all of R. And we're taking the integral over all of R of these rational functions. And so these will be amenable to the to partial fraction decomposition methods, but you can find that the residue theorem allows you, in some circumstances, to make quicker work of the computation. So here's the setup. So basically, you want to compute this this integral. So our integral negative infinity to infinity p of x over q of x dx, that's the limit as big R goes to infinity of negative R to R p of x over q of x dx. And to do this integral, so the clever thing is that we're going to apply this kind of idea. So what you're going to do is you're going to consider, so we're going to consider, we're going to extend these polynomials to a complex variable. So that's going to be our function f. And we're going to consider a particular curve in the complex plane. So our curve, so we have the x-axis, the imaginary axis, and our curve is going to be this semicircle with a straight segment here. So this, it's going to go out to R here, to negative R here, and this is going to be part of a semicircle of radius R. So this is going to be our curve gamma. And we're going to apply the residue theorem to this curve gamma, and that's going to tell us what the value of the integral around gamma is. And then we're going to take a limit, and that'll give us the value of the integral that we want. So basically what we have here is that the residue theorem gives us that the integral around gamma, right, so the integral around gamma of p of z over q of z dz, that's equal to, so you have two pieces. One is just the piece on the real axis, so that's just negative r to r, p of x over q of x dx. And then the other piece is, so let's say that this upper bit here is gamma sub r. So then we have the integral along gamma sub r of p of z over q of z dz. And that, by the residue theorem, so this is equal to the sum times 2 pi I, the sum of the residues of p over q at some points wj, some singular points wj. And what are these singular points? Well, they're the singular points that are inside this this curve gamma here, right? So you have singular points inside gamma, and those are going to be the zeros of q. And you see, q is just a polynomial, so it can only have finitely many zeros to it. And so an nth degree polynomial can't have more than n zeros. And so since there's only going to be finitely many, we can always just take our r big enough that that the zeros of q, which are in this upper half plane, are contained in this semicircle here. So we'll always just assume that our r is big enough that it contains all of the zeros of q, which are in the upper half plane. So this sum over wj, this sum over the Wj in the upper half plane as such that Q of Wj is equal to 0. Okay, so that's how we get this constant on the right hand side here. So what we're going to do is look at this formula, and we want to take the limit as r goes to infinity. So you want to take r goes to infinity, and what we're going to get out of this term is the integral we want. On the right hand side, we're going to have some quantity which is easy to compute without integration, and then the final bit is that what we want to see is we want to hope that this term here goes to 0 as r goes to infinity, so that that's something we don't have to compute. Right? So what we're going to get is that the integral of negative infinity to infinity of p of x over q of x dx equals 2 pi I times the sum of the residue of p over q wj, where this is over wj such that the imaginary part of wj is greater than 0, so those wj are in the upper half plane. This is if the integral over that half of a circle of p of z over q of z dz, if that goes to 0 as r goes to infinity. And so we'll just look for some condition that guarantees that that integral goes to 0 as r goes to infinity. So looking at that, so the integral over gamma r p of z over q of z dz, that's the integral from just parametrizing 0 to pi. Z is r e to the it, and so dz is I r e to the it dt. Okay, and so let's call this quantity ER. Or actually, before I do that, let's write this out a little bit more explicitly. So let's say P is our polynomial. It's an z to the n. So this is going to be r to the n eit to the n plus ... plus a naught over, and let's say q is b sub m. Let's say it's an mth degree polynomial, r to the m e to the it to the m plus ... plus b naught, and then we have I r e to the it dt. And so let's call this e sub r. And what we're going to do is estimate e sub r. So the absolute value of e sub r, that's less than or equal to, so the absolute value of an integral is less than or equal to the integral of the absolute value. So just slapping absolute values on everything, we have this I r e to the it, the norm of that is just r. Then we have the norm of an r to the n e to the it to the n plus ... a naught over bm r to the m e to the it to the m plus ... plus b naught, absolute value, and then dt. And what we'll do is, in the numerator, I'm going to pull out effectively a z to the n. So I'll pull out an r to the n e to the it to the n. And then the norm of the e to the it to the n is just going to be 1. So what we'll see is that we have 0 to pi. So pull the r to the n out. The e to the it to the n, that gets killed by the absolute value. So we have now inside the absolute value an. Then we have an minus 1 over r e to the it plus ... plus a naught over r to the n e to the int. And then we have, yeah, let me just combine this r here, I guess, with the r to the n. I'll just say this is r to the n plus 1. And then doing this similar thing on the bottom, pull the r to the m, e to the I, t to the m out, and get b sub m plus b sub m minus 1 over r e to the I, t plus dt. And then when r is large, so we can make all this stuff here. And so everything here is going to 0. Right? So this is all going to 0. So we can make r large enough so that all of that in absolute value is less than 1. Right? So let me apply that. So 0 to, let me pull the r's out. So we have r to the n plus 1 minus m, integral 0 to pi. The numerator, we have absolute value of a sum, so that's less than or equal to the sum of the absolute values, absolute value an, and then plus all that other stuff. You can make that less than 1 by just using, by taking r sufficiently large. And so this is for r large enough. Okay, and then that the rest of that stuff in the denominator there. So again, you can make this pretty small, like as small as you want. So we can take r large so that this is smaller than, so that the norm of this is smaller than, say, half the norm of bm here. So what I can do is, using the reverse triangle inequality, this will be bigger than the absolute value of absolute value bm minus absolute value bm over 2. Okay, so all this in the blue box, I can make that as small as I want. In particular, I can make it less than half as small as bm. All right, and now that's just the constant times that inside that integral, so I get just pi times norm an plus 1 over norm bm. I have a factor of 2, and then we have, so that's all just some constant, and then we have r to the n plus 1 minus m. And remember, the goal is we're looking for this to go to 0 as r goes to infinity. So what we want is for this to be a negative exponent here. Right, so we need n plus 1 minus m to be negative, so we need n plus 1 to be strictly less than m. And since n and m are integers, we can say that we want n plus 2 to be less than or equal to m. Right? So this is the degree of q, the denominator, and this is the degree of p plus 2. Right, so we need the degree of q to be to exceed the degree of p by at least 2. Right. All right, so that gives us a method. So computing, so integral of negative infinity to infinity p of x over q of x dx, that equals 2 pi I times the sum residues p over q wj. So these wj are the singularities which lie in the upper half plane. If the degree of q is at least 2 bigger than the degree of p. Okay. So that's a situation. You can compute that indefinite integral by this method. if that one condition holds. So here's an example. So as an example, we can look at the integral from negative infinity to infinity of x squared over 1 plus x squared times 4 plus x squared dx. And so here the degree of p is equal to 2 and the degree of q is equal to 4. So degree of p plus 2 is less than or equal to the degree of q here. So we can use our method. And so this is 2 pi I times the sum of the residues of p over q, wj, where the wj, the imaginary part, is greater than 0. So we need to find the singular points of our rational function where the imaginary part is greater than 0. So just in the upper half plane. So clearly our singular points here, so the singular points are clearly plus or minus I and plus or minus 2I. Right, so the ones in the upper half plane are I and 2I. Right, so we're going to have 2 pi I residue of p over q at I and 2 pi I times the residue of p over q at 2I. Okay, and to do that, again, we can use our formula where we write our function f as some analytic function over some power of z minus the singularity. So what we can do here, so our f of z, so let's say f of z is that's z squared over z squared plus 1 times z squared plus 4. And so one thing we can do is we can write this f of z as, so looking at the residue at I, so focus on the I. So I can factor that z squared plus 1 as z minus I times z plus I, and then leave the z squared plus 4 alone. And focusing at the I, our k of z becomes this function here. So we just, since our m is 1, we just have to, we get a 0th degree derivative. In other words, just the function k itself, we just evaluate that at I. So we have 2 pi I times I plugged into that function circled in red there. So we have minus 1 over 2I times 3. Right, so this is negative pi over 3. So this will be negative pi over 3. And then we have 2 pi I times, well, on the other hand, we can write our f of z as z squared over z squared plus 1 times z minus 2I times z plus 2I. And then focusing on 2I, that in blue, that will be our k of z. And so plugging 2I into that k, what we get is minus 4 over, let's see, minus 3 times 4I. Right, so what do we find? So our I and I cancel, the 4 and the 4 there cancel, and then the negatives cancel into positives, and so we just get 2 pi over 3. And so it looks like we get pi over 3 as our final answer. Okay, so this indefinite integral works out to be pi over 3. Okay, and there's another simple example in the book. So integral negative infinity to infinity dx over 1 plus x squared squared. You should so read this example in the text, or try to compute it yourself. So read in text or compute yourself using this method. Okay, so that's another example. So we can try our hands now at something more interesting that doesn't have a general method. So before we had some rational functions satisfying some kind of condition. We had a uniform method that worked for all types of integrals like that. But here we just are going to look at an isolated example and see if we can't make something work using the residue theorem. So we have cosine of x over x squared plus alpha squared. And here alpha is just some positive real number. Okay. So the basic thought is to kind of use the same idea. So you want to try to use the same basic idea as before. With the rational function, so we can just try to take f of z to be cosine of z over z squared plus alpha squared, and we can take gamma to be, and so in our plane, we can take gamma to go like this around there. All right, and we see there our only troublesome point is going to be when z is equal to I times alpha, right? So we'll have our sort of singular point at I alpha, right? And so we should be able to apply the residue theorem to figure out what the integral around that curve is, and that should give us some information if we take the limit as r goes to infinity, right? So this is going to be r and negative r. That should hopefully give us some information about our integral. We might be able to compute our integral like that. So the problem here, so let's again say that this upper half circle is gamma sub r. The problem with this approach is that the integral along gamma sub r of cosine of z over z squared plus alpha squared dz does not go to 0 as r goes to infinity. And basically that is because, so before we had a polynomial p over a polynomial q, and we assumed that p had a significantly less degree than q, right? So as z became large, then that's going to mean that q is much greater than p. So in that case, our integrand is becoming quite small as r goes to infinity. And so that's why that integral went to 0, roughly speaking. But here, our cosine, so cosine in the imaginary direction is a hyperbolic cosine, and that is an exponentially growing function. So essentially what you're going to be looking at is exponential over polynomial, and that's going to grow too fast, and that this integral is not going to approach 0 as r goes to infinity. So this is basically because cosine of z is exponentially large. Along the imaginary axis in the imaginary direction. Okay, so we can't use this function, so we can't just substitute imaginary values in for our, right? So we can't change just x to z and expect this to work in quite the same way that we did before. But there is no reason to give up hope, so don't give up. So what you can note is that, well, Right, we're just trying to compute this integral. We're not obligated to pick this as our f of z function. We can pick whatever function is convenient to us as long as it's somehow related to the function that we're trying to integrate. So we're not obligated to use cosine of z over z squared plus alpha squared. We can use any function as long as it's related to cosine of x over x squared plus alpha squared. So one thing we might notice, so basically the trick is to think of this cosine of x as the real part of e to the ix. Okay, so what we'll do is we're going to consider f of z to be e to the iz over z squared plus alpha squared. Okay, and so that's the function we're going to integrate over that curve. So what we find here is that the integral along gamma of e to the iz over z squared plus alpha squared dz, so we have the integral from negative r to r of e to the ix over x squared plus alpha squared. So that's the part along the x-axis, along the real axis, and then plus the integral along gamma r of e to the iz over z squared plus alpha squared dz, and that has to be equal to the residue at the one pole of our function, which is going to be at I alpha. So we have 2 pi I times the residue of our function f at I alpha. And, well, to compute this, so just write f. So f is e to the iz over z minus I alpha times z plus I alpha. Right? And so, again, just as by the method we've done before, you're just going to plug I alpha into this. Right, so we get e to the minus alpha over 2I alpha. And so we get pi times e to the minus alpha over alpha. Okay, and so what we'll find is that the integral from negative infinity to infinity of e to the ix over x squared plus alpha squared. So here we're taking the limit. So look at this. That's equal to this, that constant. So we'll take the limit as r goes to infinity. So this first thing here, that becomes our indefinite integral. And then that will be equal to pi e to the minus alpha over alpha if the limit as r goes to infinity of that semicircular integral goes to 0, if equals 0, right? Okay, so again, we can call, so let this integral here, let's call that e sub r. And so we can estimate e sub r. That is, so we'll estimate and we'll, so we have to parameterize. So it's going to be integral from 0 to pi. And our z is r e to the it, so capital R e to the it. So we have the norm of e to the I times z, and the z is r e to the it. And then we have r squared e to the 2it plus alpha squared. And then dz is ir e to the it, but the I e to the it just has norm 1, so this is just r dt. Okay, and so what we can do here, so this is, okay, so let me say, so less than or equal to, so let's pull the r out, integral 0 to pi. The denominator, using the reverse triangle inequality, right, that denominator is going to be bigger than or equal to the norm of the first thing, so that's r squared minus the norm of the second thing, so that's just going to be alpha squared, as long as the absolute value of that. So as long as r is large enough, so as long as r is bigger than alpha, so this is, so assume r is bigger than alpha, that denominator is going to be bigger than or equal to r squared minus alpha squared, and so the 1 over that denominator is less than or equal to 1 over r squared minus alpha squared. And then the numerator, so we have the norm of e to the I, so just fill in the definition of e to the it. So this is r cosine of t plus I times r sine of t. Norm of that dt. And what we get is, so when we distribute this I, the e to the I r cosine of t, that's a unit complex number, so that's going to go away in the norm. And then when we distribute the I there, what we're going to get is, so we have r times r over r squared minus alpha squared. We have e to the minus r sine t dt, integral from 0 to pi. Okay, and to compute that is just a little bit of a lemma. So the result of the lemma isn't something I would memorize. It's just more the method of doing this is interesting. So we have the following estimate. That this integral is less than or equal to pi over r times 1 minus e to the minus r, where r is some constant greater than 0. And the proof of this lemma is the following. So integral from 0 to pi e to the minus r sine t dt. By symmetry, so since sine looks the same in the interval 0 to pi across pi over 2, right, when you reflect it, it doesn't matter. So we can basically double up, so we can do double the integral from 0 to pi over 2. So this is the, by symmetry of sine around pi over 2 on the interval from 0 to pi. And so like the area under the curve of sine has the same curve profile, just reflected across pi over 2 on that interval from 0 to pi. So I think you probably know what I mean. Okay, so we can just do that. And then on the interval from 0 to 2 pi, so we want to estimate this from above. So so I have this negative here. So sine is positive on 0 to pi over 2. So this negative, that's a negative quantity. So to say that negative quantity is less than or equal to something, I want to say that sine of t is greater than or equal to something. And so looking at the graph of sine of t on 0 to 2 pi, one thing, so 0 to pi over 2. So here's pi over 2. One estimate I can make is that sine is bigger than or equal to that line that connects the point 0, 0 to the point pi over 2, 1. So the slope of that line is 1 over pi over 2, which is 2 over pi. So this is greater than or equal to 2 over pi times t. so substituting this into this integral, we have e to the minus 2r over pi times t dt. Right? And then I can actually integrate that exponential. So this is equal to 2 times, so we have to undo the chain rule. So we have negative pi over 2r, and then e to the minus 2r over pi t evaluated from 0 to pi over 2. And so combining this, so I'll use this negative here in the next line. The 2's cancel. I'll have pi over r times, instead of evaluate top to bottom, evaluate bottom to top using the minus sign. So you just get a 1 minus e to the, substitute pi over 2 in, and you just get, for t, and you just get minus r. Okay, which is exactly the statement of the lemma. All right, so you're basically just using that linear graph there as a lower bound for sign. That's kind of the key after a little bit of a symmetry argument to reduce the interval down to pi over 2. Okay, so returning to the estimate above, this is less than or equal to r over r squared minus alpha squared times pi over r, so that those r's cancel, and then you get 1 minus e to the minus r. So as r goes to infinity, this goes to 1, and you have 1 over this quadratic, and that quadratic goes to infinity, so this part is going to 0. So this goes to 0 as r goes to infinity. So indeed, that extra part along that semicircle does go to 0, and so our integral is equal to pi times e to the minus alpha over alpha. All right. So the last example we have time for is sine of x over x, the indefinite integral from negative infinity to infinity of this function, classic integral. And so as before, we're going to try f of z is e to the iz over z. So we'll use e to the iz for the sine part instead of sine of z. And we'd like to try again to use our contour. Right, so this is our contour gamma, where the upper part we have gamma of r, and so we have 0, r, negative r. The only problem this time is, so as where before we had z squared plus alpha squared in the denominator, so that wasn't equal to 0 along the real axis. Now we have just x, which is equal to 0 at 0, right? So we can't use this this contour because it runs straight through the singular point, right? So we have this singular point here that our contour runs through. So as before, when we ran into a problem with an idea that worked, we just modify it slightly rather than throwing it all out completely. So rather than throwing our idea out completely, we just have to avoid this singular point at 0. And so what we can do is, right as we approach 0, we'll just skirt around it by a little semicircle here. So our gamma this time is going to look like this. And let's say that this happens here. This is 1 over r, and this is minus 1 over r. So as r goes to infinity, that little semicircle gets sort of closer and closer to 0, and the bigger semicircle goes further out towards infinity. And let's call this gamma sub 1 over r. Or actually, since that's going clockwise, let's call that negative gamma sub 1 over r. Okay, and this time actually we're not using the residue theorem because our only singular point is at 0, and our curve gamma doesn't go around that singular point, right? So our function is holomorphic, analytic inside this whole curve. So actually by Cauchy's theorem, implies that 0 is equal to the integral, around gamma of e to the I z over z dz, and this is equal to the integral from 1 over r to r e to the I x over x dx plus integral from negative r to negative 1 over r e to the I x over x dx, and then plus the integral along gamma sub r of e to the I z over z dz, and then plus integral over gamma sub 1 over r e to the I z over z dz. Okay. So as before, what we're going to do is take the limit as r goes to infinity. So as r goes to infinity, these two together are going to make up our indefinite integral that we're interested in, and we have to figure out what's going on with these other things. So let's look at first that one. So the integral around gamma sub r of e to the I z over z dz, that's the integral from 0 to pi of e to the I r e to the it over r e to the it, and then dz is I r e to the it. So the r e to the it's cancel, and you're just left with I times integral 0 to pi e to the I r e to the it dt. And again, just as before, you can estimate, so you can estimate as before, and the details are almost exactly the same. We handled this before. You just use the definition of e to the it, and when you apply the absolute value to estimate the integral, you just get e to the minus r sine t, and then you can estimate that using the lemma above, and what you find is that this goes to 0 as r goes to infinity. Okay, so now what we have to do is figure out what's going on with the integral along this smaller semicircle. Oh, right, excuse me, this was actually negative gamma I r. So what we have to do here, right, so let me summarize so when we take r goes to infinity, what we're going to find is that the integral from negative infinity to infinity of e to the ix over x dx is equal to the limit as r goes to infinity of the integral along gamma sub 1 over r e to the iz over z dz. So the negative here, I just put that on the other side of the equation. That becomes a positive now. And then we take the limit as r goes to infinity, and we have to see what we get here. And notice that this is, so whereas the limit of this integral here went to 0 as r goes to infinity, this cannot be 0. This limit here is not going to be 0. That's not going to be 0 as r goes to infinity, because if we take a look here, this is the integral negative infinity to infinity of, so we have cosine x over x dx plus I times the integral from negative infinity to infinity of sine x over x dx, right? And this is the integral we're interested in. And this integral here, we know, is just going to be equal to 0, because this function that's in the integrand here, cosine is even, but x is odd. So you integrate an odd function over negative r to r, that's going to be equal to 0. So basically from the definition, this integral is going to be 0. So what we're going to get is, on the right-hand side in this limit, we're going to get some purely imaginary number, and the imaginary part of that imaginary number is going to be our indefinite integral that we're interested in. So what we have to do is essentially we're looking at our singular point 0, we have this little half an arc, gamma sub 1 over r, going along that arc. And the arc is shrinking, so as r goes to infinity, that arc is shrinking towards 0, and we have to ask ourselves what that value that we get in the limit is. So a suggestive guess, so a good guess is that what we're going to get is I times pi. And the reason is that if we take the integral, so here's 0, if we take the integral around a full circle, that is just, so if we take this integral, that integral is just the residue, right? So we take this integral, right? So just going to use the picture to denote the integral. That's going to give us the residue, or 2 pi I times the residue of e to the iz over z at 0. And that's just 2 pi I times e to the I times 0. So that's 2 pi I. So you take the integral around the full circle, you get 2 pi I. So this half circle here, as we shrink closer and closer to 0, that half circle should sort of give us half of the contribution of the residue, because the residue is kind of a local quantity at 0. So in that limit, as we go to 0, since we're covering half of that limiting circle, we should get half of this residue computation of the full integral. And so that turns out to be true. So basically with this, so if this guess of I pi is true for this limit, then our integral is going to be just pi, right? Because this limit is equal to I times the integral we're interested in. So let's say here that if true, then the integral from negative infinity to infinity of sine x over x dx is equal to pi. Okay, so actually, yeah, so it turns out that this is true in a rather strong way. So let me write down a lemma. Okay, so here's the lemma. It says that if you have just merely a continuous function, not even analytic, at z0, and you have a small arc of a circle, the arc having theta naught radians, and the circle having radius delta, excuse me, I wrote epsilon there, then in the limit, as you take delta going to 0, the integral along that arc, so let me make it clear, the arc is the green part there. Yeah, so the limit as you draw that arc closer to z0 is I times theta naught times the value of f at z0. And when theta naught is equal to 2 pi, we proved this earlier in the semester. So that's the case where you have a full circle of small radius, which is shrinking to z0. So we proved that earlier in the semester. And if we just apply this lemma up here, and so you see that so your r goes to infinity, that's equivalent to your 1 over r going to 0. So your 1 over r is your delta. So I'm looking at this up here. And so if we just apply this with f equal to 1 over e to the iz, then we get I times pi times e to the I times 0. So in other words, just I pi, which is exactly what we were claiming. So the result that the indefinite integral here is pi will follow from this, directly from this lemma. And the proof of the lemma is to just look at the difference between these two quantities. So first, let's take a look at gamma sub delta f of z over z minus z naught. Let's let our z be z naught plus delta times e to the I t. And t is going to go from, so let's say that this angle of inclination here, so in the picture, So let's say our angle of inclination starting is alpha. So we're going to go from alpha to alpha plus theta naught. Okay, so this is integral from alpha to alpha plus theta naught of that denominator just becomes delta e to the it. The numerator is f of z naught plus delta e to the it, and the dz is I delta e to the it. So the delta e to the it's cancel, dt, and you get the integral from alpha to alpha plus theta naught of I times f of z naught plus delta e to the it, dt. And so now we look at the difference between this and the quantity I theta naught f of z naught. So I theta naught f of z naught, well, theta naught is the length of that interval, right? So the theta naught f of z naught, that's the same thing as integral from alpha to alpha plus theta naught of the constant f of z naught dz, right? So if I look now at the difference between this quantity and this quantity, the two that I'm claiming are equal, and I take the absolute value, that'll kill the i's, and so I have the absolute value of alpha, integral from alpha to alpha plus theta naught of f of z naught plus delta e to the it minus f of z naught d. Oh, excuse me. I'm sorry. This z here was supposed to be a t. So that's dt, and then I can estimate that using the absolute value of the integral is less than or equal to the integral of the absolute value, alpha plus theta naught, absolute value of f of z naught plus delta e to the it minus f of z naught dt. And then this integrand, that's less than or equal to a constant, which is just the max of, so we're looking at, so we have z naught, we have this arc at a distance of delta. I can just say, well, I can just look at that solid disk, right, that entire solid disk, and say that the difference of those values is less than or equal to the, so the max over the closed disk around z naught of radius delta, say closed disk, the max of f of z minus f of z naught. And so z in that closed disk, and then the length of that interval was times theta naught. Right, so we have this constant. So that integrand is less than or equal to that constant, and that constant is going to 0 as delta goes to 0 by the continuity. Right, so every value in that disk, as that disk shrinks to z naught, is getting arbitrarily close to f of z naught. So this quantity, so this max quantity is going to 0. So this goes to 0 as delta goes to 0 by continuity. Continuity of f of z at z naught. Okay, so that generalization of an earlier lemma, a lemma from earlier in the semester, gives us the last little piece that we need to conclude that our indefinite integral was equal to pi. And so we applied the residue theorem to kind of guess what the value of that integral that we were over that little half arc was, and then that suggests this lemma as a generalization. Okay, that is all we have time for. So there are some interesting applications of the residue theorem into computing definite integrals, and the book has a lot of other examples, many more examples than we have time to get to. So that's all for now.